Okay, shall we get started? I guess we're starting a bit late. I'm going to try to keep it to 80 minutes. Okay. All right, so my name's Nick. I'm a researcher at Microsoft Research in Redmond. And I'm going to tell you over the next few days about the system that I've been building with several people called Fstar, and how we use it to verify low-level code for security and correctness properties. I'm super happy to be here. I was a student here in 2004, and it was awesome then. I think it's still awesome, maybe awesomer. So do interrupt me with lots of questions along the way. Let's try to keep this interactive. I'll try to pop a couple of questions at you as I go. All right, so program verification. So back in 2004 when I was here, program verification, maybe Rustin was alluding to yesterday and Amal a bit this morning, ComCert hadn't come out yet. It was still 2 years to go till ComCert. Program verification seemed like way out there. It was like this crazy dream that no one, we wouldn't really get to, let alone get to 2 years later with ComCert. And since then, there's been an amazing amount of progress in program verification, to the extent where these days you can expect a team of experts to produce realistic, deployable, fully verified artifacts, still with considerable effort, but it can be done, and can be done at scale. And I think there's been a number of successes, but the successes are kind of divided into two camps. And on the right here, you have left. Here you have proofs that are done using interactive proof assistance, things like Coq or Isabelle or Agda, things like that. And using these tools, people have proven ComCert or the SEL4 operating system, mathematical proofs like the four-color theorem or the Fate-Thompson theorem. And one characteristic of proofs on this side are that they're proofs done using very expressive, dependently typed logics, where you can state pretty much any statement, any property you like in math. But the programming language that you use to express these properties is, in some sense, impoverished. You only can prove things about pure total functions, the logic of pure total functions, and that's all you get. The proofs are interactive. You're trying to write detailed sort of tactics and ad hoc automation to get the proofs to go, but you sort of roll up your sleeves and do it yourself. On the other side, you have semi-automated verifiers of imperative programs. Here, the general characteristic, things like Daphne, the stuff that Rustin was telling us about yesterday, is that you have rather expressive programming languages. They have effects and so on, are first-class citizens in these languages. You have exceptions, state, sometimes concurrency, asynchrony, these kinds of things. They're built into the language. But the logics that you have to reason about programs is relatively impoverished. You have first-order logic extended with theories like arithmetic and so on. And the trade-off here is that because you restrict the logics, you can get effective automation for it using the advances that have been made in SMT solving for the last 2 decades. And you can get mostly the proofs still require quite a bit of work, but you get a good degree of automation from there, from the tools. And you have a number of successes here, things like the Verve operating system or the Ironclad system from Microsoft that's been doing verified distributed systems using Daphne and SMT solvers. But I think there's this gap between the two. You kind of want, what I hope we would have sometime in the future is a system that lets you get the best of both worlds. You have rich programming languages with higher order functions, but effects also as first-class citizens. And you can reason about them using SMT solvers and get good automation when that's possible. But there's a kind of a seamless, as seamless as one can hope for in some sense, transition towards very expressive logics where there's still no limit in some sense. You can still prove any theorem you like in math with commensurate effort. But you get automation for the relatively easy common cases. And that space, I think, is a really fruitful space in which to do research. And Fstar is squarely in that space. I think there are other systems trying to explore this space too. And I think it's a great space to to think about for all of you too. So what is Fstar? Yep. Yeah, I said you get very effective, you get very rich programming languages. You get higher order functions, you get effectful programs, you get all of that, but the logics are somewhat impoverished. So the point I'm making is that you want, the stuff on this side is very rich logics, but very poor programming. And the stuff on that side is very rich programming, but rather poor logics. So Fstar is a functional programming language with effects. It's like OCaml or F# or Haskell. And it extracts, in fact, to OCaml and F#. I'll tell you about how Fstar extracts some more in a bit. It's got a semi-automated verification system using SMT, inspired by things like Daphne and so on. But it's based on a core logic that's really got its roots in dependent type theory. So its core logic looks like Coq or Agda or Lean. In fact, it actually looks a bit more like New Perl, as I'll tell you in a bit. It's kind of an extensional type theory. And it's got in addition to doing proofs by SMT, it's got a meta-programming framework where you can do proofs using tactics. Also like Coq and so on. So to give you a first taste of what Fstar looks like, this is a really kind of hello world in Fstar. You can write code in ML-like syntax. Actually, let me pause here for a minute. Let me take a quick poll of the room. Like, how many people here have programmed in typed functional languages before? OCaml, Haskell. Oh, all right, great. How many of you have programmed in typed functional programming languages that have richer types, Agda, Coq, this kind of thing? All right. What about untyped functional programming languages, things like Racket? All right, excellent. Okay, so that's good. So I can show you a pile of syntax like this, and I don't have to explain syntax at least, right? Okay. So you write programs in ML-like code. Here's a factorial in OCaml syntax, which in this fragment also happens to be Fstar syntax. And you can give it a specification, and here's a spec that you can write in Fstar that you can't write in, say, OCaml. It says factorial is a function that takes an integer, n, refined by this predicate here, that n has to be at least 0. And it's a total function. Arrows are total, meaning the code doesn't diverge. It has no effects. It's a really pure mathematical function. And it returns an integer, and this integer is at least 1. Okay? And you can ask Fstar to check it, and it'll use the SMT solver and check it and say it's all good. Behind the scenes, what happens is that with respect to a prelude that defines the semantics of better? Okay? So behind the scenes, with respect to an environment that gives semantics to integers, multiplication, these kinds of things, that's a primitive prelude. You write factorial, you write any term, Fstar and a claimed type for it. Fstar is going to build a typing derivation for it. And the shape of the typing derivations are such that they end with a verification condition, a guard. And the way you interpret this is to say, if this formula phi is valid, then this typing derivation is sound in Fstar. And this formula phi is fed to an SMT solver through an encoding of Fstar's logic into the logic of SMT solvers. And if the SMT solver can prove it, you trust the SMT solver, and you can conclude this theorem. Okay. Having verified your program, you have a number of choices for how to run your programs. By default, you write an Fstar program, and you can extract it to either OCaml or F#. And in the process of doing this compilation, Fstar is going to erase all computationally irrelevant parts, all the proofs, all the specifications. You're going to end up with just an OCaml program with OCaml types. Now, it turns out that Fstar's type system is much richer than OCaml's. So there are programs that are typable in Fstar that are not typable in OCaml. So during this translation, Fstar, at those points where the program fragments are not typable in OCaml, it will insert obj.magic, OCaml casts. Okay, so this is kind of what Coq does too. Coq programs extract to OCaml, but not all Coq programs can be typable in OCaml, so you get obj.magic during the extraction. So one way in which I like to see this is that Fstar morally is extracting to untyped lambda calculus, right? But in fact, OCaml with obj.magic is untyped lambda calculus, right? So, but OCaml knows how to compile untyped calculus really well. So we go there and we compile to OCaml, and you can link with OCaml libraries and so on. There's a subset of Fstar called Lowstar, which is a first-order subset of Fstar in which you make memory management explicit and object layouts explicit. I'll tell you a lot more about Lowstar. And if you write in Lowstar, we have a backend called Kremlin. KR meets ML, right? You get that? KR, who's KR? Right. Okay, so this is going from ML to C. So Kremlin translates Lowstar programs to C, and you can compile your C program using any C compiler. You can use CompCert if you like. But most people tend to use GCC because it's faster, much faster. And there's a subset of Fstar called Veil. And Veil is an assembly language embedded in Fstar. And you can extract assembly programs, Veil programs to assembly language of your choice. It's a DSL in which you can specify the semantics of x86 assembly or ARM assembly and so on. And you do your proofs at this level, and you extract programs to run down at the bottom. Okay. So some uses of Fstar. So these days there's an umbrella project called Project Everest that's been running for about 3 years. And it's an effort to use Fstar to build and deploy a verified HTTPS stack. So HTTPS is this protocol that I'm sure you've all seen when you go to your bank or something on a website. The URL box in the top of your browser says HTTPS with a little green lock next to it usually. And that says that you're using an encrypted connection with the server. That protocol is kind of the linchpin of internet security. But it's been hit by many kinds of bugs and crypto flaws, protocol design flaws, implementation bugs over the last 20 years. So we're building a verified implementation of the core protocols underneath HTTPS. And that's mainly, the main protocol there is called TLS, Transport Layer Security. So we're building an implementation of that in Fstar. In order to build that, so our implementation is called MeTLS, Microsoft INRIA TLS. It's a joint effort between us and INRIA and some other places. In order to build that, we are trying to build a verified implementation down to the lowest level cryptographic assumptions. We're building verified implementations of crypto primitives in assembly where we need it for performance. We build other implementations in C. Our protocol stack is in C. So we have several sub-projects that are building verified components. And maybe I'll just highlight a couple. We have a project called EverParse that builds verified parsers and formatters for network formats. I'll tell you a bit more about that later. It's like a parser generator for network formats. And Everest Crypt, which is a verified crypto provider. Our verified code, several pieces of this are deployed in production code in several places. So Firefox, if you're running Firefox these days, you're using our crypto to negotiate TLS connections. Windows uses our crypto for a new protocol called Quick that's coming up. The Linux kernel has a library called Zinc, which is going to be the default crypto provider in the Linux kernel. That uses verified crypto, our verified crypto, as well as some others, actually. There's Adam Tripalla's group at MIT is also contributing to Zinc. Windows Azure has a blockchain where the main Merkle tree that implements the blockchain is fully verified in Fstar using our tools and libraries. Several open source blockchains, Tezos and Concordium, use our verified crypto. So you can build and deploy performant verified crypto using Fstar, but I think you could also do this kind of stuff in many other tools out there. I think to me, it's amazing that this is even possible these days. It didn't used to be just a few years ago. So let me tell you a bit about Everest Crypt, just a couple of slides. Evercrypt is our main crypto provider. A crypto provider implements a suite of crypto algorithms and constructions and packages it in a way that that does several things for you. So for instance, there are many ways in which you can do hashing. There's SHA-1, SHA-2, there's SHA-2 256, there's many hashing algorithms. At some level of abstraction, protocols are independent to the particular choice of the hashing algorithm that you intend to use. So for instance, I don't want my high-level crypto proof to depend on the specifics of SHA-1. So I just want an abstraction layer that says the protocol is going to negotiate a particular choice of algorithm, but the rest of my proof can be done parametrically in the choice of these algorithms. Evercrypt provides this layer that lets you multiplex between different implementations and different choices of verified algorithms while verifying the algorithms themselves down to C in assembly. And the way we see it is Evercrypt is meant to be our sort of no excuses verified crypto library. So anything that goes into Evercrypt, it has to be fully verified. Verified, I think the bottom of my slide is chopped off. It says verified for memory safety, functional correctness, and side channel resistance. And its performance has to be at least as good, if not better, than the best implementations out there today, unverified implementations, better than OpenSSL, right? That's the bar we aim for. And right now it's about 180,000 lines of code and proof that extract to 40,000 lines of verified C in assembly. So you should see it as, we're getting 40,000 lines of code out of it, but we had to sort of write nearly 5 times as much code and proof to get the job done. So it's still a lot of work, but 5 to 1 is, compared to some other efforts that if you do proofs totally interactively, sometimes these ratios can be more like 20 to 1. So that's kind of where we are right now. And to give you a sense of this sort of no excuses performance thing, so can't see this too well. I think the resolution is sort of off a bit, but I guess you're zooming in. I am zooming in, but anyway, never mind, I can read it to you. So this is a graph that, so people have been doing verified crypto implementations now for at least last, say, 5 to 8 years. And this is a graph showing the performance numbers of various efforts in producing verified crypto since 2014. That's time on the years on this axis. And this is gigabytes per second, the kind of performance that that each of these verified implementations provide you. Not all papers that actually do verified crypto report their performance numbers, but these are several of the ones that actually do. Now, OpenSSL, its best implementation for AES-GCM, which is this primitive that secures 90% of internet traffic. So you have to have a good implementation of AES-GCM to be plausible. This OpenSSL is doing 6.5 gigs per second, okay, using hardware acceleration from Intel. In 2004, this is a paper from our group, and it's somewhere, close, well, it's way off, right? Things are kind of getting better. This is a paper also from our group, 2017. We're sort of in the half gigabyte a second range. Earlier this year, we had a POPL paper. We hit 1 gigabyte per second. We're really happy about that. Soon after, there's a group from India and INRIA that's gotten a little bit better. And then now we went past OpenSSL finally. So we're really happy about this. So at this point, there's really no excuse to not use our verified implementation. Then the way we did it was we essentially took the OpenSSL code. The OpenSSL implementers, there's this guy, Andy Polyakov. He's incredible. He's incredibly smart. He makes bugs occasionally, but he's also, extremely skilled at producing low-level verified implementations. And we essentially reverse engineered his code, figured out what are the invariants that he had in mind for implementing this code correctly, and proved that those invariants were in fact sufficient to prove the correctness of this. So I don't know if Andy Polyakov had these invariants so precisely set up in his head. Perhaps he did. But in a way, what we did is that we discovered the invariants that justify Andy Polyakov's optimizations and make it go that fast. So I'm just telling you about the work of a large team. There's a photograph of some of us. That's not all of us, but some of us recently gathered at MSR Cambridge. This is a joint effort from MSR, INRIA Paris, Carnegie Mellon, MIT, the University of Rosario in Argentina, and many former members. There's lots of us working in this space. And it's all open source. We welcome contributions. If you're interested, please reach out. We'd be happy to work with you too. Okay, so what's this talk about? So I want to make the point that sometimes, and I make this point a little bit, how shall I say, a little bit reticently at OPLSS, at the church of Lambda in some sense, right? At some point, sometimes you have to stoop to writing low-level code. And you have to do this for performance. And the crypto community is kind of obsessed with performance. Security is something that, people, they really want it, but they really don't want to pay for it. So, it has to be performant. They want this 6 plus, essentially 6 gigabytes per second means that you're encrypting at it's sub-cycle per byte. Okay, so for performance you need this. Now, here's another point which is, I think, a little bit counterintuitive. I think in order to get security, you need to write low-level code. Now, we often think that this is not true. Like, hey, if you don't want buffer overruns, just write in a high-level language, get rid of a bunch of security problems. And that's true to a certain extent, at least for those kinds of problems. But for crypto, the security bar is significantly higher. You also need to worry about things like side channels. And if you're writing in a high-level language, forget it. You're never going to prove anything much about side channels. The GC is going to kick in a case where you have a JIT around. The JIT's going to kick in. The abstraction between you and the machine is too far for you to be able to reason about low-level attacks. So I make this somewhat perhaps controversial argument that sometimes for low-level code, for security, you really need to be also low-level. But specifying and verifying effectful programs is hard, particularly at this low level. And like I said, you tend to write more proof than code, 5 times more proof than code in our case, right? So it pays to try to structure your specifications as best as you can to reduce the proving overhead. And here's where I think our community can help. Functional programming is, for me, the science of abstraction. One way in which I think of it is that functional programming, for me, is really about the freedom to abstract. You should be able to abstract over anything in your program. Lambda is one, and the mechanism of abstraction is Lambda. And it gives you the freedom to abstract over everything in some sense. In a pure type system, it lets you abstract over terms, over computations, over types, over modules, over everything. You should be able to abstract over everything. And for me, that's what functional programming is. And in terms of figuring out a way to structure your specifications, that's really about what are the right abstractions for writing your specifications so that proofs go smoothly. And I think functional programming is the answer there. So a core Fstar design principle is that we have a type of computations. Computations describe effectful stuff, computations that have effect. Okay, so that's state or network, sending messages on the network or diverging or these things. But these computation types are indexed by algebraic structures of various forms. And those algebraic structures, they obey some equations or some theory. And you reason about the computations through the proxy of their indexes. And by proving some properties about their indexes, you can conclude some properties about the underlying computations. That's the kind of, at a very abstract level, that's the kind of design motto of Fstar. So there's 3 examples that I'm going to try to get to in this talk. The first is weakest precondition inference. So you're writing an effectful program. If you want to feed this thing to an SMT solver, the verification conditions to an SMT solver, and you want it to be, wanted to look, say, something like Daphne or VCC or an effectful program verifier, you need a way to build a verification condition, this formula phi that I had on the side for factorial. And you need a way to do that in a way that's kind of generic in the effect. And I'm going to show you that weakest precondition inference is really about monads and continuation passing style. Okay? There's imperative data access. You write a lot of code that's going to, read some value from some piece of memory, and you want to view this raw read that's maybe just reading at some offset into a buffer as some structured memory access. And in the functional programming community, we know how to do structured memory access over arbitrary structures, and our mechanism of doing that is lenses. And we'll see how you can reason about these low-level data accesses in imperative code using high-level structures like lenses. And the third thing is parsers. So in the functional programming community, in Haskell, for instance, the way you do parsing is using something like parsec, a parser combinator library. And what we're going to do is we want to parse wire formats of network messages that are coming, that we just get from, the other side of a TLS connection. And there's two things that rate limit a TLS connection. There's the crypto, that's the first bottleneck. We've kind of got that under control. It goes fast now. The second thing is a lot of what you do is just parse and format network messages. That's the next bottleneck. You want to make that go fast too. So we want to parse and format raw data on the wire, minimizing the number of copies that we make. Copies involve memory allocation, that's expensive. And the way in which we're going to structure these parsers and formatters is by using insights from parser combinators in functional programming. So we're going to read raw data from a network packet, but from a perspective of a specification, it's just going to look like applying a parser combinator. And I'm going to show you what that looks like. And I think there's many more such structures still to be discovered, and this is where I think the fruitful intellectual work is, in finding how to reason about complex low-level programming patterns using simple, well-understood mathematical high-level structures. Later in this week, I'm going to tell you, I think tomorrow I'm going to tell you about how we model and prove cryptographic security. And then I'm going to tell you a bit about the sort of lift the cover on Evercrypt a bit and tell you how we actually program and verify efficient crypto primitives. And then the fourth lecture is a little bit open. Let's see how it goes. I could tell you about a few different things depending on your interest. There's, in terms of things that you might try outside of the lectures, there's this Fstar website where if you go here, fstar-lang.org, there's a tutorial. And it's a tutorial that runs in your browser. So you can sort of type Fstar code in on this side and ask it to verify it. And so I encourage you to try this. If you're, the first 6 or 7 chapters, I think, are fairly self-contained and will give you a basic introduction to how Fstar works. So that's something you can try. There's lots of exercises sprinkled throughout. Also, Fstar is on GitHub. All our development happens in the open. And just for you, we did a new release just today. Okay, so check it out. Back to here. Right, any questions so far before I dive into the technical stuff? Okay, so I'm going to start with a tour of just the functional core of Fstar, and then we'll get to effects. So informally, at its core, like I said, it's like a type theory, like Coq or Agda. Some of the main features that it has that are, I'm going to highlight a few of them that you may not have seen if you've only been programming in these other systems. The first one is refinement types. Refinement types are kind of a proof-irrelevant sigma type, for those of you who that may mean something to some of you. But one way you should see it is that it's a type refined by a formula. So the type nat in Fstar is defined as the refinement of integers that are non-negative. Okay? But the thing about this being proof irrelevant is that the proof of this property is never materialized. It's a squashed proof in the way in which we this phrase is from New Perl also. The way we think of this is as a squashed proof. We never actually materialize the proof because the proof is done by an SMT solver typically, and that means the representation of a NAT is the same as the representation of an int. It does not have. If this were a sigma type, sigma types are a pair of the underlying carrier and the proof of the refinement. And that pair has to be destructed each time you use a sigma type. That's not the case with refinement types. A NAT is just an int, but has this additional property. We have recursive functions. Those are primitive in Fstar, and that we already saw factorial. Refinement types, the way they're introduced and eliminated is just by subtyping. So for instance, times here, multiplication, is defined on integers, not just natural numbers. But I have a natural number n here, and I'm applying n to times. And this just works because nat is a subtype of int, so I can use subtyping here to just type this multiplication. I don't have to explicitly eliminate nat. It just happens via subtyping. Logical obligations, like if I claim that factorial is returning a nat, the way Fstar works is it builds a typing derivation that analyzes the structure of this program, and then in each case, it has to prove various properties. So, for instance, in this branch, it has to prove that 1 is a nat, right? Because factorial is returning 1 in this case, it has to be a nat if factorial is a nat. And the proof obligation it gets is, well, for 1 being a nat, that's easy. That's just a leaf proof that constants that Z3 can prove. And here, it has to prove that n times factorial of n minus 1 is a nat. So to type the factorial application, it has to prove that n minus 1 is a nat because factorial expects a nat. And the way it does that is that in this context, it knows that n is at least 0 because n is a nat. It knows that n is not equal to 0 because this test failed. We're in the else branch. And then in this branch, it has to prove that n minus 1 is greater than or equal to 0. Well, that's a tautology. Z3 can prove it. And here, now it has to prove that the multiplication is a nat. Well, it uses the induction hypothesis that says that factorial of n minus 1 is a nat from the typing of factorial. And then it has to prove that that is a nat, which it can also do. Okay, SMT is good at that kind of thing. So those are refinement types. The refinement types sort of fit into a broader framework of dependent types. And dependent types are, the main construct is dependent product, or pi, or dependent functions. And the way I see it is that dependent functions have a codomain, that's a result, that depends on their domain, right? So here's the codomain, y of type integer such that x is less than y, and this x is the domain, is the value in the domain, okay? So that's why it's dependent. And this is the increment function. And here's one type for increment. It says increment takes an integer x, it returns an integer y such that x is less than y. Okay, but there's many types for increment. Here's another one. This is kind of maybe the most precise type you can expect. It says increment takes an integer x, returns an integer y, where y is exactly x plus 1. That's the kind of the full specification of increment. But there's many types for increment. Someone want to tell me some other types for increment? Yep.
You can do greater than or equal.
Greater than or equal, or not equal, or all sorts of things, right? So refinement types are not principled in some sense. There are many types that you can have for a program. Okay, then we have inductive types. Here's simple inductive types like list. Here's list in Fstar and map over lists, and lambdas. You can map a lambda over a list. All of this just looks like OCaml, right? But you also have inductive families. So here's vector. Now, if you've looked at dependently typed languages before, this vector example is often sort of trotted out as like the first example. It's I don't know if you've come across this before, but it's also usually the worst example in many dependently typed languages. Right? Have you tried to program this in Coq? it's kind of painful because you have to do a lot of munging about indexes. You have to show that you typically have to write a lot of coercions to show that, for instance, if you're going to do append of lists, that the addition commutes in some sense, and you can sort of shift things around, and you have to apply a coercion to do it. And if you do other kinds of index structures, like, I don't know, let's say you want to do red-black trees using an index type like this, it's usually a really bad idea to do your program this way in Coq. The way in which you do it in Coq usually is to say, I'm going to write a simple ML-type data structure without indexes that are not going to capture these kind of invariants. And then I'm going to write a program that's going to do red-black trees. That's also going to be like an ML-like program. And separately, I'm going to write a theorem that tells me that it maintains whatever the red-black invariant I'm interested in. And that's because type systems like Coq and Agda and so on are based on, at least my take on it, it's because it's based on intentional type theory, where these systems make a very careful distinction between how definitional equality and provable equality work. Definitional equality means that two terms are related to each other by reduction. Okay? By beta, whatever reduction machinery you have in your language. Beta, eta, perhaps sometimes, fixed point reduction, pattern matching, whatever reduction machinery you have, two terms are definitionally equal if they are related by reduction. Separately, you have some notion of provable equality that says two terms are propositionally equal if you can build a proof that they are equal. They don't necessarily have to reduce to each other. And these two notions are kept separate in intentional type theory. These days, with some good sort of, I think, a good sort of, perhaps initially unexpected consequences. By keeping these two things separate, for instance, you can do homotopy type theory quite naturally in something like Coq or Agda. Because in something like homotopy, one of the main ideas is that equality proofs have a lot of computational content, and we want to separate definitional equality from provable equality and reason about things carefully that way. But this separation of provable and definitional equality comes at a price, and it means that you have to do all these transports and coercions and so on in many places. In Fstar, we don't do that. We say, okay, provable equality and definitional equality, you can conflate them. The benefit of that is that you can write code like this without any coercions. Things like these index structures, they work very simply in Fstar from a programming perspective. And at the cost of, well, you're probably not going to do homotopy type theory in Fstar. That's okay by me, but that's just a disclaimer in some sense. It's also higher order over these index structures, as you'd expect. So the Fstar functions we saw so far, they were all total functions. Okay, and so that in some sense concludes my very brief tour about the functional core of Fstar. Now we're going to start looking at effects. So when I write A arrow B, this is just sugar in Fstar for something a bit more elaborate that says it's A arrow tote B, and this is the effect of the computation that's latent under the arrow. Okay, when you apply the function, you get a computation, and that computation happens to be total. Okay? So nat arrow nat is really just an abbreviation for nat arrow tote nat. Okay? So let's see, suppose we try to give factorial this type. What do you think would happen? Yep.
Would it not work because you could pass in a negative number and it would just go forever?
It would loop, right? So factorial is not total on all integers. It's only total on the non-negative ones. And if you gave this type, tried to give this type to factorial, Fstar would complain at the n-1 saying, hey, I expected an integer x that was, and I'm going to tell you about this symbol, that was less than n in some sense, but it couldn't prove it at this point. So what is this symbol, double less than? So termination checking in Fstar is based on a well-founded ordering over Fstar terms. And this well-founded ordering, Fstar is configured with a certain ordering to begin with. You can define your own ordering. If you can prove it well-founded, you can use that order. But by default, Fstar comes with this order, which says that natural numbers are related by less than. Negative numbers are unrelated, okay? Because well-founded orders are about no infinite descending chains. The negative numbers clearly don't have that. Inductive types, values of inductive type, yeah.
And what about one positive and one negative? Do you relate them?
What? No. You could.
Sometimes that's useful because you dip down a little bit into the negative number. It's key to it.
I mean, what you do then is you shift everything up.
But you may not know exactly how much you should.
So, this is what Fstar comes with in the box. But you can do any well-founded order you like, so long as you prove it well-founded. And we have a library that lets you do that. Like we have a way of, you model, say, the general framework for that is we have accessibility predicates in Fstar. So I don't know if that's a way of modeling well-founded orders in type theory. Like such libraries exist in Coq too. Such a library exists in Fstar. Proven sound against the Fstar, without any axioms. It's part of Fstar. Provable in Fstar. And then you can do that order if you want. Then we have, so I have to say, Ruston, a lot of these ideas are from you. So thanks, right? I mean, a lot of this well-founded ordering stuff I got from talking to Ruston a lot. Ruston and I were down the same corridor from each other for a long time. And this is a lot like what happens in Daphne, at least at first order, I think. This one, maybe not. So this last one says, so inductives are related by the subterm ordering. There's a notion of lexicographic ordering on lexicographic tuples. And then there's this one that you need at higher order that says that the result of a total function precedes the function itself. Okay? And these ordering constraints that Fstar builds are discharged by the SMT solver. So to give you a sense of how this one works, lexicographic tuples, here's the Ackermann function, which you can prove terminates. But the reason it terminates is because on every recursive call, the arguments to Ackermann decrease according to this lexicographic order. So let me try to spell that out for you. So if you look at Ackermann, it takes two arguments. If you want to prove that it terminates on all branches, the first branch is easy. There's no recursive call. Okay? The second branch, Ackermann, is called on two arguments. The first argument decreased. The second argument is not related to the first one at all. But m-1 precedes mn in a lexicographic ordering because the first component went down. And then you don't care about the second component if the first component went down. Right? And here's the tricky one. Here we did Ackermann, calling it on m again. So m didn't go down. And if we were expecting m to go down on every recursive call, then this might not actually terminate because that didn't decrease. But it didn't increase either, and the second argument went down. So that's good. So that means that m and n-1 are still less than m and n in the lexicographic order. Ackermann returns something huge. And we're using this huge thing to call Ackermann again. But we don't need to worry about it. It's not going to diverge because the first argument went down. Right? So that's how lexicographic orderings work. Yeah, this is kind of maybe the canonical example of where you might need lexicographic orderings. Do you have questions about that? Yeah?
Can you infer that without having to specify?
Yeah, we do, but the inference is in this case is very trivial. So we have just defaults. The default, if you don't write this, what Fstar does is it says the termination metric for this function is all the arguments lexicographically in the order in which they appear. So that default, there isn't any particular smart inference. That default happens to work well for Ackermann. It also happens to work well for most other programs. Yeah.
Is it possible to specify more complex termination metrics?
Sure.
Okay.
Yeah. And I might show you some of that. There'll be some examples of that over the course of the week, for sure. I lied a bit earlier that I said I was making a transition to FX, but here is my transition to FX. I was still telling you about total functions. The Fstar type system is stratified into two pieces. There's, is that a question? Yep.
So this is somewhat unrelated. It's like to a previous question that someone asked.
Okay.
You said that the reason Cock and Ackermann requires you to manually discharge by hand obligations related to preserving the invariant of red lines.
Yeah.
Do you think you would be able to recover the automatedness of Fstar if you hooked up a SMT solver to Cock or Ackermann and then asked whenever you had an invariant obligation, send it to Z3, somehow reify that into a proof back to Cock or Ackermann? Is that an option?
It's plausible. I think it gets quite delicate because these things these coercions that you insert, they disturb the term. So you may lose certain equalities because the term is no longer the one that you wrote. It has this additional coercion in it, and that thing may block reduction in some places. And it's an interesting direction to pursue. I've thought about it a few times, and I've always been like, it's a bit hairy, but it's an interesting problem. It's worth thinking about. Yeah.
So when you use SMT, right? But SMT comes with some sort of limit. So there are first order propositions that you cannot prove
Yes.
just by SMT. So what happens?
Yeah. In that case, SMT is not the only means by which you prove Fstar programs. If the SMT solver fails, you could write a tactic, you can write a proof term, you can do anything.
So I guess the question is, so let's even assume SMT is not able to prove the inequality over the function over vector.
Yeah.
So what does that mean?
What do you do then? So you can, you just have to have an equality in the context. You have to somehow be able to prove an equality by any means. Let's say you write a proof term and then you can stick the equality in your context. Using that equality, you can then rewrite the term just by Fstar's rewriting. You don't have to hit it with the coercion. If you're in a context where, say, n equals 5, vector of n is equal to vector of 5. So you don't need a coercion for it. Yeah?
If you want to try run some program in machine learning like k-means, it's hard for you to know how many times you can get converged.
Yeah.
Or you can assume that between two paths, the result is close enough.
Yeah.
But even you know that it's close in some distance, but you cannot to predict how many times you can get this, or you can gather.
Yeah.
How do you prove that?
So I think, do I understand your question correctly? You're saying that sometimes you really want to write divergent programs.
Yeah.
Yes. Am I going to tell you that in a second? Yeah, I totally agree with you. Sometimes you want to write divergent programs. If you want to write a divergent program, you're out of luck. In Fstar, you can write a divergent program and encapsulate it from a pure program by saying, oh, this thing has an effect. Don't treat it as a proof, because it may not actually be a proof. It's really just computation. But you can still prove things like partial correctness about your divergent program. If it terminates, then some property is true. Or as it executes, it always maintains some invariant. You can still do partial correctness proofs about divergent programs. Anything else? Okay. Okay, so we have two classes of types in Fstar. There's value types, or the types of unconditionally total terms. These are things like int or list of int and so on. And we have computation types that are the types of computations that are divergent, perhaps, or manipulate state or these kinds of things. And the Fstar effect system encapsulates effectful code from pure code. So pure code can call effectful code, but not vice versa. And the general form of the dependent function type in Fstar is really like this. It says it's a function from a value x of type t to a computation. And a computation, there's a variety of computation types that you can have here. Tote is one of them. Okay, so we saw that, can I reduce the, I think maybe I can recover some space by doing that. Is that still readable, or it is? In the back? Okay. So there's refined value types. That's this kind of refinement that we've seen. But there's also refined computation types, and that's what comes next.
Okay, I'm sorry, that's no longer readable.
Okay. Okay, there's that last line just said they're refined. You're right. There wasn't that much content on it. Okay, so I don't think you missed much. So how do you add effects to a functional programming language? There's the classic way of doing it is by encoding effects as monads. So here's a kind of bog standard state monad in Fstar. St of A is a function from initial states to results and final states. Okay, there's a return and a bind for this monad. The bind is just doing sequential composition of stateful programs. And there's two actions, a get and a put. Get lets you get to read the current state, and put lets you update the state. Okay. Happy to take questions about this. I mean, let's say, I mean, you may not have seen some monads before, but let's want to encourage you to ask questions. Don't. Yes. They are online. Yeah, this code is online. It's this slide deck is reachable from the Fstar website. Yeah. And it gets so you write a state monad like this, and you want to turn it in Fstar into a computation type that lets you program with state primitively. You don't necessarily want to execute your programs this way. You want to run against, let's say, a primitive heap, as opposed to just threading state values. So to do that, you say, hey, I want a new effect, state. This is an abstract effect in Fstar, and it says, this effect state, its representation for reasoning purposes, is given in terms of this state monad. Okay? And now, having done that, you can use the actions from the state monad just without any do notation or anything. Fstar for stateful terms is called by value. And actually, one thing that I don't know if when I understood this maybe some years ago, I was surprised by it as well. So monads come into functional programming by some work by Eugenio Moggi. And in a way, one thing I didn't appreciate for a while was that Moggi was not trying to add monads into a functional programming language. He was trying to describe the semantics of call-by-value functional programs using a framework of monads. What happened then was that monads became a way to sort of structure functional programming with effects in many functional programming languages, including Haskell and OCaml and many others. But initially, monads were there as a way of just explaining the semantics of call-by-value. Okay? And that's what's happening here. Fstar is call-by-value for effectful terms. And here, this monad is just explaining the semantics of this call-by-value. It's not actually being used to run the call-by-value, run monadic terms. Okay? So you should read Moggi's initial papers again. They're actually quite accessible. Yep.
So if I try to, I would define monad in Coq by also adding the rules or bind the rules.
Yep.
Like for instance here, if you write something bad for bind,
yep,
you can still define near text state.
Yeah, so this is a kind of a concrete language design question. So what we do is when we do this, we typically prove on the side that they satisfy the monad laws. That's good. It's good good hygiene, I would say. Something you should do. Fstar does not insist on it. Yep. Yeah?
Are return and bind necessary, or are there other ways to implement?
No, return and bind are necessary. Return and bind, yeah, yeah. So you write terms like this. This is call by value. You don't need any do notation. And Fstar is going to infer for this program the type unit, arrow, state, that's this abstract state, unit, and some specification W. I'm going to tell you about this W. So type inference in Fstar includes inference of weakest preconditions. Okay? And when Fstar makes that statement, like it infers this typing judgment, what it really means is that W is a weakest precondition predicate transformer that describes the semantics of E. So let me try to spell that out a bit more. So what does a weakest precondition really mean? It says, just informally before reading the slide, it means that if you want to prove some postcondition about your program, the weakest precondition is going to tell you what precondition you have to prove about your program, such that the validity of that precondition ensures that when the program runs, at the end, you're going to get your postcondition. Okay? Seeing heads nod, that's good. Okay? So here's spelling that out a bit more. So what it means is that, prove this in Fstar, what it means is that for postconditions, if you can prove the weakest precondition W in the initial state, so the weakest precondition applied to the postcondition is a precondition. So if you can prove that precondition about the initial state, E in the initial state, it's going to result in a final state such that the postcondition is true of the result in the final state. Okay? So let's stare at this a little bit more. Let's parse out. If we want a statement like this in a way, it forces the type of W in some sense. So what is the type of W? So the type of W depends on the effect, it depends on state. In this case, the type of W is a stateful WP, STWP, parameterized by a result A. And it's a function from a postcondition about A's to preconditions. Okay? That's what weakest preconditions are, from post to pre. Okay? Where the postcondition on A is a predicate relating the result to the final state. Okay? And the precondition is just a predicate on the initial state. So it's a, okay, I'll let you stare at that for a minute. Do you have any questions about it?
Where is the weakest type?
Good question. It doesn't, not here. It doesn't have to be the weakest. If Fstar concludes this, there's a subsumption rule that says W need not be the weakest. It may infer something. Fstar will infer the weakest, but through subsumption, the programmer can say, no, I want something actually a little bit stronger than that. And this judgment does not tell you anything about the weakest. Yeah.
Define what it's supposed to be the weakest precondition, like involved weakest terms, or somehow makes the weakest steps?
I think it would involve saying something like, for any formula, any proposition that implies this, that formula also implies WP of post. Right? So anything else that you can use would be at least as strong as this one. Okay. So this guy, there's a paper I wrote in 2011, 2012 or something like this, where it introduces this idea, and I called it the Dijkstra monad for state. So in a way in which I see it is that Dijkstra was giving kind of weakest precondition semantics to various kinds of imperative programs. And this is kind of casting weakest precondition semantics into a monadic framework. And so these are, there are several papers about Dijkstra monads now, if you want to read about them. Yeah? This box is meta. This is not Fstar. This is meta.
And in that meta, did you intend that to be a function or a relation?
This is in the case of state, it's a function, but if the effect were, say, non-determinism or something, then it would be relation.
Okay. So in that case, the quantifier, even in meta, should also quantify, it should somehow say whether this is a possibility for the post-state, or if you always hold it.
Yeah, so we actually have, there's multiple ways in which you can set it up. We have Dijkstra monads for non-determinism. They can be either angelic or demonic, and you get different WP interpretations for them. So let's stare at this a little bit more. I mean, what is this WP inference thing, really? And I think it's actually really very closely related to continuation passing style, okay? So let's look at this guy, and think about it, like, look at this, A arrow S arrow prop, arrow S arrow prop, okay? So this is the continuation monad. Continuation monad it's got some result type R, so an answer type R and parameterized by an A, okay? And the continuation monad is A arrow R, okay? That's saying, if the continuation is a function that's going to consume the result of my function producing an R, then the continuation monad is applied to this thing is eventually going to return an R too. Okay. Now let's look at this guy and let's rewrite it this way. I'm going to try to derive STWPA from here. So if I have S arrow, the continuation monad, now the result type for the Dijkstra monads is prop. It's the continuation into propositions, because it's a logical thing. So if I take S, the continuation monad into prop, over A star S, that's the result type of my computation. It's a state monad. If I expand things a bit, I get S arrow, that's just inlining that definition there, A star S arrow prop. This guy is equivalent to this guy just by swapping, by permuting the order of arguments on an arrow. So it's A star S arrow S arrow prop. But hey, that's just what I want, right? That's ST post A arrow ST pre. That's STWP. Okay? So the Dijkstra monad is really like the continuation monad. Okay? Now one more step. Now I think I cut this time I need to show you the bottom of the slide. Can you see back there? Maybe you can't see back there. I'm not sure what I'm going to do. Can I zoom into this part of the slide? Okay, I'm going to just try to read it, okay? So this is we've almost recovered all the structure. There's still, or let me put it this way, there's still more structure we can recover from this. So let's look at it some more. So the state monad transformer adds the state monad to any other monad. Right? So the state monad transformer from M is parameterized by a monad M. It says state T of MA is S arrow M of A star S. So the state T of MA is just a state monad on the outside, but the computation here may also have some other monad M inside it. Okay? And now this looks like that. This looks like S of the continuation monad applied to something. So this really is the state monad transformer applied to the continuation monad with result type prop. Okay? So WPs are really just the WP for a particular effect, say M, is really the M monad transformer applied to the continuation monad. Okay? And I didn't know that a few years ago. I was really happy to find this. I think it's cool. So Fstar actually automatically derives that now. So if you write down this monad, like this, the plain vanilla state monad that we had before, it's going to derive a weakest precondition transformer monad for that monad by effectively doing something that amounts to, for a class of monads, we know how to automatically find their monad transformers. So for exceptions, for instance, it would look like, I think I can zoom in again. It would look like the exception monad transformer applied to the continuation monad with result type prop. And that would look like whatever type of exceptions you have. Let's say it's options. Option A are a prop to prop. And you can combine this. You can combine state and exceptions and get combined WPs and so on. I'm not going to show you that. Okay, pause, yeah.
So in this example where you're combining different sort of like monads or effects,
Yeah.
you still get the nice like sort of compositional, like without having to write do notation or anything like that,
Yeah.
that you had from before, or
Yeah.
does it get a little bit messier?
You don't have to write, you do get the combination. So the way it works is that if you can define a collection of effects, and then you can define morphisms or lifts between them. And so I can say lift exception to state, or state to exception plus state. And then Fstar is going to insert those lifts for you during type inference. So you don't have to write them by hand. Other questions? Okay. There are some coherence conditions in those lifts. I mean, you can't have, say, if you have two lifts between state and state plus exceptions, then Fstar is going to say, hey, I don't know which one to apply. So, okay, so WPs are a nice kind of framework for inferring specifications about your programs, but they're actually not really the nicest way in which to write specifications. That's like, in a way, as I've kind of tried to make the case, WPs are really about continuations. And continuations are notoriously hard for, I think, humans to read about. It requires you to kind of flip things around backwards. And you don't want to write specifications using WPs. You would prefer to write specifications using something more like Hoare triples. So, but Hoare triples can be easily defined on top of WPs by something like this. So this says, I want, instead of writing state computations everywhere, I'm going to write a derived form of ST computations where I'm going to index my computation by a precondition and a postcondition rather than by a WP. I have two indexes instead of one. And I can just define this by saying if I have STA of pre-post, that's really the same as state, which expects a WP. And the WP can be built this way that says it's a lambda, which for all continuations K, and initial states S0, I need to prove my precondition. And for all results X and final states S1, if I prove the postcondition relating the initial state, the result, and the final state, then, I mean, assuming that postcondition, I have to prove the continuation. So I can build Hoare triples on top of WPs. Okay? And then things like get and put be given specs that are maybe more familiar than WP specs. So here's what the spec of get and put look like in Fstar. We have a bit of sugar where requires and ensures. They actually have no semantics in Fstar. They're just tags that are there to help you read. So ST, the type of get is that get is a function that takes unit. And it's an ST computation returning an S, that's returning the state. It requires nothing. The precondition on the initial state is trivial, you can always call it. And it returns an S that's called result, and it's related to the initial state and the final state by this formula. S0 equals result, and result equals S1. The state didn't change, and it returned to you the current state. Okay? And put is the converse. It takes a state, you can always call it, it throws away the initial state, and sets the state, final state S1 to, oh, that should be S, sorry, not S0. Okay? I think I was aiming to stop at 12:20, so I have about 10 minutes more. Or we could just stop. I mean, I don't want to, if you guys are getting hungry for lunch, I could still have 3 more lectures. I don't want to overload you. So show of hands, who wants 10 minutes more about how you model refs and whatnot, okay? Who wants lunch? Okay, the next few slides are about how you model a richer model of state in Fstar. Rather than these monolithic state monads, you actually want references and allocation and assignment and deallocation. I have about 10 minutes about that, or we just go to lunch. 10 minutes, okay, cool. You'll get it anyway. You'll just get more of this tomorrow. So you don't want just this monolithic get and put. You want a richer model of state, and with dereference and assignment and whatnot. And the general philosophy here is that you kind of write effectful programs. Again, you model the state using effectful libraries in Fstar, and then you can write stateful programs like this, and you can extract them just to primitive effects in ML, because the libraries have been used as a model of the ML memory model. Okay? So here's one model for the heap in Fstar. And we have several such models. This is kind of the one slide kind of model. So we have a module called heap, and it has, I'm going to model abstract addresses as just natural numbers. And the heap is going to be an abstract type. So clients can't see its representation, but this module is going to give you some facts about it. And the heap, it has 2 components. It has a next adder, which is the next address at which you're going to allocate. And it has a map that stores the contents of the heap. And this map is a map from addresses. It's a partial map, so it's got an option there, because I still need some space to allocate, right? And each element in the heap is you should see this as a heterogeneous map. Every address in the map contains a value of a potentially different type. Okay? And the value stored at each heap address is this existential type. It says there's a type A and a value stored there of that type. Okay? Right? So these are existential types, or actually they're more like these are strong sums in Coq, or sigma types. Okay? So you can just make these heterogeneous types in Fstar, because from Fstar's perspective, they're not heterogeneous. Every value has that type, right? And there's an invariant expressed using a refinement that says for all addresses, that should be A, not H. For all addresses A, such that A is greater than the next address, the map at A is not allocated yet. So I have room to allocate. Okay? Now that's my abstract model. Now I can just define, say, ref T. Ref T is just an address, but I'm going to define this notion of containment. I'm going to say a heap H contains a ref T if the address of the reference is less than the next address, so it's still allocated, and the map at that location, it's a sum whose type T is actually the index type. So I know that if I can poke the map at that point and get back a T appropriate for ref of T. Okay? And I can define functions to manipulate the heap. I can select from a heap, given a reference that is contained in the heap, I can select out a V of type T, and I can also update the heap at that reference with a new V. Okay? Now, this is, like I said, our full heap models are much more elaborate than this. They let you do deallocation, they let you store structured values and so on. But that's the basic idea. Now, to read references, I can define bang this way as an effectful combinator that says if I have a ref T, I have a stateful computation returning a T, But I need to prove that in the initial state, the ref is still live. The heap contains the reference. And if so, I'm not going to change the heap, but the value that I return is going to be the value of the reference in that state. And I can implement this on top of my monolithic state. Because I have my monolithic state monad. The state S, I'm going to instantiate to heap. I have get and put. And I can just implement bang using get and select. Okay? And I can do assignment using get and put. I get the current state, I update it, I put it back. And I get signatures that look like the ML signatures for these things. Now, a wrinkle is that part of what, in some of our more complex heap models, these preconditions of H containing R, we have a way of just removing them. In a way, what I see, if you think about, if you interpret the ML type system kind of as if it were a proof system, then ref T can arguably be seen as a proof of T. Because the only way in which you can produce a ref T is by coughing up an initial value for it. There's no other way to build a ref T. So ref T ought to be a proof of a T. So in a way, I have a dereference function. Its job is to return a T. If it has a ref T, it should be able to return a T regardless of whether the heap contains it or not, because ref T is a proof of T. So richer memory models kind of internalize this idea, allowing you to remove these kinds of preconditions that are stable in some sense. And that's reading and writing, but since and the ML memory model does not allow you to free references, right? It's GC'd. But because we have a powerful logic here, we can add free and guard it by suitable preconditions. Now, at the cost perhaps of being forced to retain these kinds of preconditions elsewhere. Okay? But I can do freeing by saying, hey, if I want to free a reference, I need to prove that the heap contains it. I don't want to allow double freeze. Okay? So I need to prove that the heap contains it. And then what I'm going to do is the way I'm going to implement it is to get the current state and nuke that address. Replace the map at that address with none. Now to support this, I need to enrich my invariant. Because remember the invariant I showed you said that the map, actually perhaps not. The invariant, what I was confused by was that the invariant I showed you said that the map above the next address is none. But it didn't say that the map below next address is all sum. Right? So I'm free to nuke addresses beneath the allocation counter, allocation limit in some sense, and still satisfy my invariant. And so that's how you do free. Okay, so I think I'll stop there. And